In this section, we're going to talk about the final two number sets and square roots. So we talked about rational numbers before. Rational numbers can be written a over b, where a and b are integers. So it's any number that can be expressed as a fraction. That's a rational number. If you write it as a decimal, it will either repeat or it will terminate. All of these fractions, these rational numbers, as decimals will either have a repeating pattern or they will just stop completely. Okay. There are some numbers, though, that you can't represent as fractions, and if you try to represent them as decimals, they never terminate. They just go on and on and on forever, and they never have any kind of a repeating pattern. So those are called the irrational numbers. So ir, that beginning, means not. So you have rational numbers, and then you have irrational numbers, and those are basically the two big number groups: rationals and irrationals. So irrational numbers are those numbers that cannot be represented as a fraction, and as decimals they do not terminate and they have no repeating pattern. They just go on forever and ever and ever. The best example of this is the number pi. Okay, pi, I even have a little pi button on this calculator. That's pi. Now, of course, it looks like it stops here because the calculator screen is only this big, but that's one of those numbers that just goes on and on and on forever, and there's no pattern, and the numbers never stop. They just keep going. There are mathematicians that have devoted their entire lives to determining all of the decimals of pi. E, little e. Now, that's not on this calculator, but, oh, well, maybe it is. This little e right here. Let me go. If I go to e to the 1, let's see, second e. There we go. That's the E number. 2.718. It's roughly 2.7, but that's where it is. I finally found it on here. It keeps going. It looks like it's got a pattern. It does not have a pattern. It keeps going on and on forever. If you ever remember in college algebra, exponential functions like e to the x, that's what this e is. It's called Euler's number. But it stands, it's like pi. It stands for a fixed value. But it goes on and on forever, so that's irrational. The square root of 2. If I take the square root of 2, I get this weird number that goes on forever. It's not like a perfect square. Square root of 17, again, I get this crazy number that has no pattern and goes on forever. If it was a perfect square like 25, when I square root it, I would get a nice number. But we're talking about the ones that when you take the square root, you don't get a nice number. Those fall under the irrational category. And if you take all of the rational numbers and all of the irrational numbers and you put them together, you get the big giant real number system, which is what we study in this particular course. We just study the real numbers. So all the rationals and irrationals together create the real number system. And we can also start talking about square roots. So the square roots of 4, like if we write square root of 4, there's actually 2. There's 2 answers. It's plus n minus 2. Because if you take 2 and you square it, so 2 times 2, you get 4. And if you take negative 2 and you square it, so negative 2 times negative 2, 2 times, you also get positive 4. Those two negatives become positive. We call the positive one the principal square root, and the negative one is literally just called the negative square root. But if you see the word principal in there, they mean the positive one. And that's the one that we use most of the time. Like in most real world examples, the positive one is the one that we use. So that's the principal, like the most used square root. So the formal definition of a square root is if a is any non-negative number, then the principal square root of a, denoted square root of a, is the non-negative number b such that b squared equals a. So for example, like the square root of 25 would be 5. That's this number b, because if you take 5 and you square it, you get 25. That's what this is saying. So the principal square root is just the positive one. Notice when we write a square root, we don't write a number in this little V-shaped divot here. If you don't write anything, it's implied that it's a 2. So that would be a square root. But what if you wanted some other root, like a cube root or a 4th root or a 5th root or a 6th root? Well, then you're going to have to put a number here. That number is called the index. And a, the thing sitting underneath the square root, that is called the radicand. So when it's mentioning this word radicand, it's talking about this number a. That's the radicand. So if your index is even. So if you're finding a square root or a fourth root or a sixth root or a 10th root or whatever it is, you cannot have a negative underneath for your radicand. So like the fourth root of 81 is what number could you multiply by itself 4 times and get 81? And you can play around with it. You don't have to go very far to figure out that it's the number 3. 3 times 3 times 3 times 3 is positive 81. If you multiply a number an even number of times, it's not possible to get a negative. If all of these numbers are positive, when you multiply them 4 times, you're going to get a positive. If all 4 of these numbers are negative, these 2 will make a positive, these 2 will make a positive, it'll all turn out positive. So for even roots, you have to have a positive underneath here. For odd roots, you can have a positive or a negative. So for example, the cube root of 8, what number multiplied by itself 3 times gives you 8? Well, it would be 2 times 2 times 2. Positive. Positive, positive, positive makes positive 8. But you could multiply a number times itself 3 times and get a negative 8 if you made the number negative. Negative 2 times negative 2 times negative 2 is negative 8. So you're allowed to have a negative as your radicand if it's an odd root, like a third root or a fifth root or a seventh root. It's just, it has to be positive if you have an even root.